I'm thrilled that you could all kind of take a few minutes to listen to us today, whether joining us live or catching up on the replay afterwards. My name is Michael Haig. I'm the head of product marketing at Yugabyte, the company behind our open source distributed SQL database, YugabyteDB. So we're passionate about our technology at Yugabyte, and I personally always love kind of presenting on it, talking about what's new. But today's a particularly special event. I mean, as I'm joined by two impressive industry veterans that are going to give us some great insights. One from one of the world's leading financial companies, and the other, of course, our very own co-founder and CTO to give us some insights kind of behind the curtains. My role here will be simply to serve as a moderator today, so don't worry, you won't have to hear me talk too much or go too much onto my marketing pitch onto why Yugabyte, but I just want to kind of be here to facilitate just a great story. So that's enough for me. Let's jump in, and we'll start with kind of proper introductions. As I've joined, as you can see, from two great presenters. I've got Dmitri Farafonov, the VP and fellow architect at Fiserv, as well as, of course, Karthik Ranganathan, the CTO and co-founder of Yugabyte. But let me let them both say a few words to introduce themselves. First off, Dmitri, thanks so much for joining us. We're excited to hear your story and journey. So maybe just kick off with a few words and introduce a little bit about your background.
Sure. My name is Dmitri. I work for Fiserv. Currently, as a fellow architect, I do a lot of research and development, working with vendors, evaluating vendors, helping out. As you know, Fiserv is in the payment industry. We have multiple lines of business. I actually work mostly on the issuer solution. So there's an acquiring side of business, issuing side of business, and financial industry. So I mostly work with issuers. It's mostly a back-end processing, but we are sharing our experience with acquiring. With Fiserv, we collaborate quite a bit internally. All the modernization and all the research efforts are shared. So I actually have a development background, so I can also answer any development questions if anybody has. But I'm here to share our story of how we actually do database selections and how we work with Yugabyte and what we came up with. So with that, I'm going to ask Karthik.
Thanks, Dmitri. Fantastic. Really looking forward to the conversation. Hey, folks out there, quick intro. I'm one of the co-founders and the CTO at Yugabyte. And like Dmitri, I have an engineering background as well. Before starting the company Yugabyte and building the database YugabyteDB, which was early 2016, I was at Nutanix working on distributed storage. So this is, if you're aware of the public clouds, it's like building a persistent disk, like EBS for the private cloud. And before that, I was at Facebook for 6 years. Very fortunate to have met my co-founders and the original engineering team at Facebook. We worked on the first generation of distributed databases. So we built an open source Apache Cassandra and worked on HBase while at Facebook, and not just building those databases, but also running them at a pretty massive scale, right? Like we're talking hundreds of petabytes of data across thousands of servers, across a bunch of data centers. So very interesting learnings. And yeah, I think our aim here is to help, Dmitri and his team, build applications in the cloud while leveraging relational technology that is cloud native, right? And so we work at it from the database perspective. So, and super excited to be here to have this conversation. Once again, thanks, Dmitri, and thanks, Michael, for hosting.
Absolutely, yeah. I mean, I think you both have, again, backgrounds not just in, again, delivering databases, but again, operating on the application side, and we'll talk a little about applications. Karthik, of course, you both wore that hat of operating and building, so we'll get that inside view. So excited to kind of have you both here. Dmitri, maybe again for folks out there that maybe aren't as familiar with Fiserv, it's a company that I think touches us more than we know. Maybe just give a little bit more detail into kind of just the role Dmitri kind of Fiserv plays in just kind of the financial industry and in our daily lives, just to kind of give some sense for kind of what you're dealing with and the importance of the applications that you work on.
Yeah, sure. The Fiserv, actually, our main business is on the acquiring side. Those are your point of sale devices. Clover is a very famous product of Fiserv. But that's not the part of business that I'm part of. I'm part of the issuing, and the issuing solution, we helping large banks and actually the medium and small banks run their credit business. And we also have a debit business offerings. So what it means is for us and Yugabyte, you guys face that challenge. We actually very multi-tenant solution. We don't just represent one client, we represent multiple clients, and we process for them. And the multi-tenancy brings a lot of complexity. Also, we in the financial industry, we are very heavily regulated. In fact, our internal regulators are stricter than external regulators. So we have layers and layers of processes that we must follow. So, and then take all of this and solve it like on a massive scale. So our online, just issuing side of the online interactions process about 15,000 financial transaction every second. We have over a billion account cards on file, and it's just very large. I often compare dealing with our type of volumes. It's like drinking from a fire hose, often compared to, right? So, and then we take our priorities as a measure stick of how we actually evaluate and work with others. So in financial services, our top priority is actually security. And our second priority is in production stability. And only then we do client satisfaction. So everything we do must satisfy the security requirement before anything else. Then we talk about production stability. Production stability often confused for functionality. For this input, I get correct output. But actually in our volumes, most problems we run into is actually in solving problem on a large scale. So scalability, high availability, a DR strategy, data replication. This is the problems that we dealing mostly. And then finally, client satisfaction is actually how fast and how quickly we can react to changes. So when we talk about the vendor selection or how we work with Yugabyte or how Fiserv selects, we always start with security. So we actually cut a lot of the latest and greatest staff, not always ready for prime time financial services application. So what you see is in the fintech, we're actually running a little bit behind on purpose because we're selecting the most secure and the most stable software to implement. And then a lot of innovation in the fintech is actually taking those very stable solution and create a right mix of them. This is why you see us doing a lot of integration work and like a lot of movement into real-time processing in the fintech, how to actually react to changes quickly. So I think what we cover today is two flavors of interaction with databases specifically. Is one, what we call the data capture. Those are just live transactions happening, and all we do is capture and copy of it. It's a lot that has to do with auditing, and a lot that has to do with actually future processing. And the second type of transaction is when is actually requires a transactionality. And this is where actually we updating. The classic example is saving a transaction that just happened, let's say in some store for a candy, and then actually being able to update the balance on the account for that money you just spent. So when we're talking about specifically in our area, how do we make a determination? Again, we're driving through our three priorities: security, production stability, client satisfaction, and then we considering all the new demands of data capturing versus actually data aggregation and coming up with the transactional records.
Nice. Dmitri, yeah, absolutely. And when you kind of think about, so you kind of jumped into the application, which is perfect. Let's kind of start at that top. You kind of talk about these kind of two different worlds: the data capture and kind of the aggregation or reporting side. Paint us a little bit of a picture of again, we'll get into the Yugabyte deployment eventually, but maybe just kind of talk about what was the state you guys were in before, kind of what was the environment look like, what were the databases that you were using? Talk a little about kind of the before picture, and then we'll get into a little bit of maybe the challenges that you faced with those.
So as many know, Fiserv and First Data merged a couple of years ago into one company, and both was very large and had their own data centers. So we actually was mostly processing in own data centers for both companies. And as you know, Fiserv was originally primarily in the debit business, and the First Data was in the credit. So it's kind of complementing products that become very large footprint. And we had a lot of presence of our services within our own data centers. And now with the modern demand of making our services available in the cloud, we start considering what are our options to run storages in the cloud. And this is where the first Yugabyte engagement was. So, and it's actually also important to understand, why do we need to move data from data centers to the cloud? When we operate on a larger scale, and we already mentioned for production stability, our implementation strategies are actually active solutions where we actively running computes in multiple regions, multiple data centers. But we also do prefer local because we do very low latency processing. And for us, hopping from one region into another, it may going from a 30 millisecond transaction to a 300 millisecond transaction. To humans, that's invisible. But for large processing platform, that 30 to 300 millisecond hop, it's 10 times loss of compute and loss of capacity. So when we're talking about the solutions that we try to implement here, we actually, as we migrate to the cloud, we not only require a data presence in that specific region where our compute is, we also require a replication, active solution where the data is accessible into multiple locations at the same time. But prefer local allow us to actually focus on the performance and try to get the zero latency without there, but the low latency processing within one region. Makes sense? So when we start engaging of why we're doing it, it's all about actually create data mobility. We also call it getting out of data jail, right? It's all about making data available to where your compute is. So, and then replication is not just cloud replication, but we're also going to be talking about what does it mean to actually do what we call a platform independence. Because what we're quickly finding out is even if we stick to just say North America regions, right? How to take the same techniques and apply them in an international scope where we go globally, right now, EMEA, Latin America, taking the same products and making them available across the globe. So now we're going not just saying I need replication for DR and high availability. Now I also need to be able to have a replication, not of the data, but replication of the product for creating a mobility cross globe. Does that make sense?
Yeah, that's great to meet you. And Karthik, maybe let me pull you in to react to that, because I know as we talk about kind of where some of the focus has been on developing YugabyteDB, I mean, those deployment options kind of going to the cloud is front and center for a lot of what we're doing. Maybe kind of give us some insights kind of maybe behind the curtains of kind of what's what kind of drove those decisions that have helped Fiserv, and then maybe a little bit of kind of where we're going with kind of this notion of kind of deployment flexibility and vision to the cloud.
Yeah, absolutely. And a great characterization, Dmitri. Like even though a completely different type of application, a different type of industry, if you really zoomed out, we did see a lot of a similar set of requirements when building cloud native applications at Facebook, right, where a number of us worked, but in a completely different context, right? And the way we solved it at Facebook was actually quite different because, you can afford a little bit of lax consistency when it comes to social media posts and likes and so on. If you get it wrong, it's okay. But you can't be too wrong about it, or you can't eventually it has to catch up, right? So in the first generation of distributed databases, right, again, back in 2007, when we started building, we realized that there was really no database available that could federate storage of data and federate compute, like query processing, right? And we, at that time, didn't even think about moving query processing close to data unless it was in an analytic context like MapReduce or Spark, one of those type of things, right? So anyway, I think we ended up building NoSQL in response to what felt like the demand of the market, but as adapted to Facebook in specific, right? And and so we ended up building Apache Cassandra, which was highly available but could compromise consistency. The first take at building anything that's distributed, because at that time, who really wants transactional data in a scale-out database? You go to a relational database for that. This is anyway the state in 2007 when there was scale, but it was mostly for certain types of data, right, that you could be lossy about. Then pretty quickly, we went to our actual messages data, which is a little more important. It's the system of record. So that became important, but our users were super happy to get any kind of database because taking a database takes a while. So they said, just build any API. It doesn't matter. Just build it, right? And we will use it. And they built their application to whatever API we put out. So Cassandra had one API, HBase had another API, and it was fine. It was okay, right? The audience we were targeting were these large tech companies who were very niche in their use cases, or so we thought at the time, right? Now, fast forward to today, the changes that have happened, at least when I look at the story of the changes inside Facebook, it kind of mirrors the story of the changes. It's like the early version of the story outside, like in the industry, where you go to multi-regions, you go to public cloud, you have compute available at the end of an API rather than people racking and stacking. You've got all of this need to replicate data, and you have a never-ending hunger for your applications to service different types of use cases and therefore to become more transactional. So it was kind of very revealing to see the dawn of a transactional big data age where you needed relational data, transactional data to work very similarly in the cloud, and not just scale out, scale in too, right? Like you don't want to keep it scaled out all the time. So anyway, so when we looked at what our users, which were other engineers in the company and even people outside in the community were asking, they wanted secondary indexes, constraints, they wanted joins. And so finally we realized they just want relational databases in a scale out world, right? Except we built two of these databases. Neither of them was architected right for, kind of scaling out a relational database, if you will, because it requires some fundamentals like distributing transactions and maintaining integrity. And so it requires all the way at the core of the database design, a different kind of approach. And we said, let's do that at Yugabyte. Let's kind of not make the shortcut we took back then, but it was not a shortcut at the time because there were no databases and people were just super happy to get any databases, period, right? Some of our other learnings along the way, right? When we started building all of these NoSQL databases, in fact, right? If you look at Cassandra, HBase, Mongo, everything was born not just before the cloud was mainstay, it was even before SSDs, right? Like flash drives were mainstay. They were all based on hard disks. So we realized that you needed a completely different kind of architecture, and you can leverage the strength of flash disks to really increase availability. So we factored that into Yugabyte. We also felt like if you're building a database for performance, which often becomes a super critical thing, as Dmitri was mentioning, low latency is important, right? You may not realize the difference as a human between 330 milliseconds or 30 and 3 milliseconds, but the machines will, and it matters, right, in the grand scheme. So we said, we have to take a C++ approach to this because we had learned our lessons with going managed memory solutions like Java. It doesn't pay out in the long run, right? So anyway, so these were some of the reasons that we focused on and bringing it to the market. And we said it's got to be open source, just like Postgres is open source and is so loved and so open, transparent, and adopted. We wanted to build literally a cloud native version of Postgres. So how do you deal with three simple things? How do you deal with resilience and availability? Because you have compute that is ready, but it's going to fail because it's commodity in the cloud or cloud native. You have scale. You should be able to leverage the compute available at the end of an API only if you can scale out and scale back in quickly. And thirdly, you have so many regions you have to replicate data. So we focused on these three things for Postgres and how would we reimagine Postgres for a world that did this way based on our Facebook experience, right? And so that's the result that you can see. And just like Fiserv, there's a lot of other interesting use cases as well. Like I think Dmitri talked about multi-tenancy, right? We recently announced a lot of folks are looking for multi-tenancy because it's a very interesting scale problem, but with a different twist, right? It's like 10 to 20% of your multi-tenant clients or tenants are really high scale. And the 80 to 90% of them are low scale, but they represent scale in numbers. So you could have 10,000 tenants that are small, but hey, it's multiplied by 10,000, so that gets big. And you have maybe 100 of them that are very large, but you don't need to multiply it by anything because they're pretty big in themselves. And you have to deal with this duality of state in a single cluster because you don't know when the small guy is going to get large or when the large guy is going to stop using it and become small, right? So it's kind of like a dynamic system. So I think that those are the fascinating things. Anyway, yeah, I don't know your thoughts on how you view the database, Dmitri, and from the application perspective, or if you had a different question for him, Michael, sorry.
No, that's perfect. Right. Let's dig into that. Let's kind of get into a little bit of, Dmitri, you hit on kind of some of the things that are important as you're looking at the data layer. I know you spent a lot of time researching a lot of different databases out there. You've kind of gone through the ringer on different technologies. Kind of let's come back to that question and maybe just peel it back a little bit more detail. I mean, you kind of talk about security being key, but as you're going through that list of features that you were looking for, that you evaluate a database against, just kind of walk us through the thought process of what's important. And then let's kind of start to get into a little bit of what was it that brought you to YugabyteDB and kind of some of those boxes that were checked off with that environment.
Also, one very, very specific question in the Q&A, I think that's for you, Dmitri, which is data replication question. Do you do active across 2 AZs or active across 3 AZs or data centers, I guess, or regions? But anyway, I would just plant that because I saw that question. But anyway, go ahead.
Yeah, I also see some questions about Clover. I just want to remind, Clover is a product of Fiserv, but it's part of the acquiring business, and I'm an issuing solution. Our product called Optis. So if you heard of Optis platform, this is what I'm working on. So this is the issuing solution, and just to speak to your examples and what we were looking for, we actually run we deal with multiple vendors all the time. You name a database, we probably have it. We ran the open source Cassandra for years. We also have a vendor managed Cassandra instances right now that we successfully using for other products. What traditional way of building software on-prem is you allocate infrastructure capacity up front. And the way it works is you predict to build a product, and you think, how many clients will be onboarded on that product? And usually you always hope for best case scenario, everyone gonna love it. So I'm gonna do a maximum capacity allocation up front. So if I need to build a database cluster, I actually gonna buy physical servers enough to manage that capacity in the future. And usually when you do a product launch, that databases sit there unused. And it may take you 3 to 4 years to actually onboard enough clients just to justify the database existence at all. So when we were moving to cloud, and this is what our conversation was with Yugabyte and other vendors were, I don't want to allocate 25 servers up front. I want to be able to start small. And as my database grow, I want to grow the cluster. So is really was the ask is only pay for what I need today in the infrastructure, in the licensing, and in the allocations of the actual compute. Now we had, and this was the question about active, we have our internal HA commitment and SLAs to our clients. The way we solve HA, we mandate within same region or within same data center replication. And then we demand cross region or cross data center replication. So today we run in 2 different regions, not 3, 2, but we replicate within the region. So we usually triple replicate in the NoSQL database, we triple replicate for local quorum. And then that triple replication replicates through another region. So we actually have 6 copies at minimum of every record. So we can always achieve a local quorum when we process locally, but we can also have entire replica in the other region. We also do active, meaning the data sets are processed and used actively, but we redirect the traffic, what we call prefer local. So if I land in one region, we're not gonna let you fill over. So what we do is we connect to the primary. It's also referred as a data center aware strategies, right? So it's a data center aware strategy with the local quorum is how we do NoSQL today. So our actually first Yugabyte solution was the port of the it's not actually a port. We built a new reporting database that we're doing a data capture. And our initial implementation was Yugabyte actually used CQL language. And for CQL, we just need a local quorum within the region and then another copy within the other region. And then there's a processing happening in both region, but there's an eventual consistency for reporting databases. So that was the first implementation. The second implementation is actually, this is where we talk about transactionality. And this is where we switch to SQL and the Postgres client. And that solution was actually what we do, we receive an intraday statuses on the account for tracking purposes. And we were actually needed an SQL transactionality where we maintain the records in the consistent state. Again, we implement in the Yugabyte specific example, what we do is you only guarantee transactionality within one region and it's an eventual consistency across the other region. And what you do is you have prefer routes where you only switch to another region in case of a DR event, a disaster recovery event. So this is active, prefer local. So you may be redirected to be constantly processing in one region or be redirected to another region actively and use the other region as your DR. But because they both actively, One is for one client, this will be a primary and this will be a secondary, but for the other one, we flip them. So this way you can achieve the transactionality in the very low latency in one region, but also have a DR strategy where you can fail lower at any time into another region.
Nice, man. Makes a lot of sense. And Dmitri, and you hit on another comment there, which again is, I mean, is core to a lot of what, I mean, Karthik and the team build, is this notion of kind of the multiple APIs. So just to kind of clarify for folks out there, you're using both the Cassandra interface and Postgres interface to YugabyteDB, correct, based on kind of the application needs?
Correct, but we don't mix them today. In the current solution, there is one specific application, and actually the applications are completely independent. So we have two separate clusters. There's a one application that does data capture. They just store data for end-of-day reporting purposes. And then there's another application that actually interacts. It's a real-time API into a tracking system. So there is a both interaction for lookups, and there's an insert coming in throughout the day. So we have scenarios where we do both, just a data capture where we do SQL inserts, CQL using Cassandra language, and then we generate reports. And then there's another application that actually uses the transactional locking of SQL. So you can do the standard CRUD operations. So you ask us about the priorities and security production stability. I believe we actually very difficult to work with on purpose. So in terms of security, and this is where the vendor selection comes in place, I think it's very hard to work with us because we demand a lot, right? And when we talk about security, it's not just how we access the data, is that there has to be access levels. And then we demand a very specific auditing requirements just for the access levels. So we audit every single interaction with database from the application perspective and from administrative perspective, and they need to be categorized. So pretty much every single SQL you run is being audited. And the difficulty coming is not was just being able to audit it, because anybody can write logs. But the difficulty comes is actually integrated with our existing system that's not even the same region, right? Because the security integration is managed by different groups, and we must submit our audit data to them for evaluation. So there's a lot of duty segregations in place. And that's why for us to bring in the vendor, we actually have to do multi-team engagement. There's an infrastructure team, there's a cloud team that works in it, there's a security team, there's an application development team, and then there is a product owners team that actually kind of submits the requirement to add that for what they want to run, and then they work with infrastructure team to make sure it runs successfully. So it's a constant balance and constant compromise of what we can do. By the way, we don't really compromise. We actually ask vendor to implement that specific requirements. So for us, the actually doing evaluation is just the first step. We actually take months of time to actually do implementation engagement. This is what we've been working out, because it's not just access and auditing, right? Then we also mandate there's encryption and transfer, which is mandatory through specific ciphers. You must satisfy the cipher list. Then there must be encryption and transfer. We don't even store the PCI data in cloud today, but we still mandate the encryption at rest. So you can see how quickly it can get complex, where you must satisfy all these requirements regardless of what kind of interactions you do. So there's kind of an engagement of where we constantly submit the enhancement. You guys must do this for me. We must implement the token authentication for application level. You must have to whatever LDAP Active Directory integration for the user management, right? So, and it's not a compromise. You can't just say, oh, I have this authentication solution, you must use it. It's in the reverse. We actually mandate implementation of certain, especially security protocols. Those are not even a compromise. So that's why it seems like it's very easy to go into, say, a cloud provider and click add button. I want to add this database. And it's just appears so. The database as a service is a nice dream. But for us, it's very hard to accomplish because We do use those database servers, but for us, there's a long checklist of stuff that I must go through. So repeating that checklist through multiple vendors is a tedious work. That's why when we talk about platform independence now, right? We really want to be able to do a checklist once and then have that solution implemented into multiple clouds, including our current talks. We're building a private cloud internally in Fiserv based on Kubernetes. And we're talking about bringing in Yugabyte on-prem and apply the same techniques on the private cloud as we do in the public cloud. So now we're talking about the actual ability to build products. We can build them internally. We can run it in this cloud, in this region. We can port it internationally in the other region. So it creates the own portability. So now the attractiveness of the Yugabyte was the fact that we actually don't code to the Yugabyte. There's not a single reference to yugabyte.org or yugabyte.com, whatever that is. There's not a single reference to any lines of Yugabyte code. We develop our application to standards. For our Java application to talk to Yugabyte, we use a JPA, which is Java Persistence API, and we just plug in the Postgres driver. That's mean that when developers don't even know they're using Yugabyte, and I know the Yugabyte, well, you probably don't want to hear this, but I can swap out Yugabyte anytime I want, and this is the ultimate platform independence. So from the application development perspective, I code to the standard interface. And it's actually the enterprise support model of how you find the vendor to satisfy your database requirements. So that creates the ultimate portability. We had problems in the past where we would develop an application to very specific database, and then there's a need to run this application internationally, and a vendor may not have support for that database in that specific region for whatever reasons. There are many legal reasons, other reasons. So now we have to rewrite the application against a different vendor just to satisfy that portability across region, right? When we code to a standard, so now I have an ability not just to say, you must implement Yugabyte database in order for me to run my product. I can say, go find a most suitable Postgres vendor in your area, right? And I know the Yugabyte has offerings going internationally in rough regions, but it's still not all 190 plus countries in the world. So the ultimate app dev approach for us is actually platform independence. So the way we write the app for the Postgres, and then Yugabyte becomes a vendor that supports Postgres for us.
Yeah, Dmitri, I mean, there's a ton there. I want to get Karthik's immediate reaction though, because Karthik, you and I recently talked about just the importance of open standards, and of course there was a big decision that was made early in Yugabyte's kind of life about going open source. So kind of what's your reaction to that, and how does that align to kind of as what's our philosophy as a company in embracing those open standards?
Yeah, firstly, I can't stop smiling like a kid in a candy store because Dmitri basically validated the thesis for why we started this thing, and super awesome to hear that. Again, going back to when we made the decision, when starting to build a database, I mean, it's no easy feat, right? Why you need to build a database? Everybody's first question is, why the hell are you doing this? You're not helping the world. You're adding one more database to the 350 databases. And if you go look at DB engines, you'll know there's literally 350 or so. And that's just pollution, and that's not helping anybody, right? But we had to build, we at least contributed to that pollution unknowingly a bunch of years earlier at Facebook, because there simply weren't databases that were cloud native, right? Like that was really the problem we were trying to solve. And we weren't really trying to solve anybody else's problem. We were trying to solve our own at Facebook. And this time around, when we looked at it, we saw that the real objection is not in building a new database. It's really in building a new database API. Because, I mean, if you take every database, you can take like Cassandra, like I think SQL, right? Like as Dmitri pointed out, or Mongo, or take any of these databases. When you say the database name, as a developer or an architect, it kind of evokes I know what that's for as a blueprint profile for that database, right? You know when it should be used, when it should not be used, when it'll you will struggle with it in the future or not, and it's going to be perfect for your use case. You know all of these things intuitively, right? It takes many years of documentation, reading, experience, building on it, operating it to finally get to that level of maturity. That many years is around 6 to 7 years, right? the people's real objection is no one wants to spend 7 years to figure out what is this animal? Does it fly? Does it run? Does it swim? Like it takes that long to figure that out, right? So one of our explicit decisions when starting the company was we're not going to force people to learn that over 6 to 7 years. We're going to give them a mental framework for saying it's just like X, but here are the changes, right? So that makes it very, very simple because you're 80% of the way there in your understanding. And this is just 20% of change that is easier to deal with than 100% new. And I don't even know what this animal is, right? So that was really our approach. So to that, what we said was we needed a extensible query processing layer where we can build a faithful replica of the databases that we choose to impersonate. But then why even impersonate, right? If the original database is good enough, we really are fixing some of the things that we have seen in our experience that are missing from the original databases. Like if you take Postgres as an example, all relational workloads, Postgres is as good a database as Oracle or SQL Server, or like some of the other folks, we could build an ANSI SQL compliant database, but ANSI SQL is not the same as Postgres or MySQL or Oracle because everybody understands these over 50 years. So we said, keep everything in Postgres, features, quirks, bugs, just keep it the same because people rely on it. Those bugs are actually features. We may say it's bugs, but it's features, right? So we don't want to change all that stuff. So we literally took the upper half of Postgres to build this. Similarly, Apache Cassandra, CQL, we literally implemented to spec to a point where you can almost lift and shift. There's about just a handful of features, a couple of features that we don't implement because they don't make sense in a transactional world. Now, we're building this, we're impersonating Postgres to make it cloud native, which means replicated, available, scalable, all of that stuff built into the database as opposed to outside. With Cassandra, you get all of that. SQL is replicated, scalable, all of that, but it's not transactional. You don't get indexes. You don't get alternate read patterns. You don't get to do a lot of other features which we have experienced are super important, like a document data type is super important in that type of a language. So we've started putting those type of things. So you could say we literally help extend the range of these databases for cloud native transactional applications by building below the waterline. Now, you obviously have to give more controls as your data extends. So we extend those languages to say, look, if you want to control as you hit scale, here are some things you can do, but it's more an extension on top of the database rather than changing the way it works. So firstly, great links to go to open API standards. And the second thing is open source. I mean, to put it bluntly, a lot of enterprises do question us even after so many years. And now I think we're seeing good success, but nevertheless, we're still small. So they question us, are you going to be around? What would happen if you're not around? Or what would happen if you start getting very expensive, like some other databases, I won't name here, but some of the databases get really expensive and people try to get off of them really badly. And what would happen to us in that case? Like if we don't want to be stuck negotiating deals or something. So open source is a hedge against all of these. Because we truly are trying to build a cloud native database revolution more than anything else, right? And then the company and the commercial side for us comes along the way. That's at least the way we think about our mission. So open source is important, both from the perspective of if we're not around, or if you need something, right, that we cannot get to you fast enough because we're small, you have full control in taking part in building the database as much as us. And we welcome it, right? So that's really one part. And the second part is, if you ever think we get expensive, the database itself is fully open. You can run it yourself, and because we're charging for a database as a service value, right? The database itself is commodity and it's free and as it should be. So yeah, open standards, open source. So yeah.
I actually, Karthik, often being asked, how did you actually solve the transactionality across multiple region replication? How do you solve, what's the difference between regional transactionality versus cross-region transactionality, and how Yugabyte is actually differs from Postgres itself? Why not just to run Postgres? So what's the actually secret sauce underneath the Postgres driver?
Yeah, great. Thanks for asking. So I'll give a high-level architecture build-up, right? Like very, very high level. So the first thing we did was we knew that we wanted it to be more. So I did this analysis on what is Postgres compatibility, because everybody kept asking about it, because we say we are, and a lot of people say they are. And we came up with like 4 levels of Postgres compatibility. At the first level, it was just driver and wire protocol compatibility, right? Like, so how can you talk to applications really easily without changing the developer drivers and so on? But then to truly make it work with ORMs, ecosystem, etc., you need the next level of compatibility, which is syntax compatibility and semantic compatibility. So, which means the exact set of Postgres commands should be accepted and should work in a similar semantic manner, both of those, right? So there's two. And then the last one is runtime compatibility, where the error messages, the failures, the quirks, the way various things work, they should all be in line with how Postgres does things. So we started, going down these layer of four stack, right? And effectively what we came up with was, it's going to be impossible for us to impersonate Postgres for the application if we built it from scratch. Well, when we were building Yugabyte in the early days, unfortunately, we'd put 6 months into building it from scratch. And we realized, good God, this is wrong. So we said, reset the effort, let's start again. And this time we're not going to build it from scratch, because we thought, okay, we built all this distributed system stuff. How hard can Postgres be? Why don't we just build it? And then we realized, oh my God, this is really hard. This is like 30, 40 years of building. So we're not going to throw that away. So we took Postgres and then we started analyzing how we can extend Postgres, right? Obviously, if you realize in a company that's been around for a year or a year and a half, early stage still, it's a lot of risk, right? Like we didn't know where we were headed and we kind of built something and now we're trying to do something else. But at that point, we realized that Postgres has a very clean architecture and down the middle where the upper half, the query processing layer, always works on tuples or rows, right? Like it just assumes that you get rows one by one. And the lower half does all these gimmicks to present stuff as rows, right? So at the highest level, we wanted the upper half to still consume as tuples or rows and the lower half to present. But that's where all the details come in, right? Because in Postgres, you can use these pointers to disks and pointers to locations of data, and you could start doing all of that stuff. And we had to unwind a number of those things and do it differently. So it was a very surgical intervention at the lower half, but the upper half remains the same. So at this point, we had a stateless Postgres upper half, which can now distribute over the lower half, but you still cannot do multi-region transactions with that because it's going to be awfully slow. It's just one single node that's handling it. It doesn't have scale. You can do multi-region, but not scalable, I guess is what I'm trying to say, right? So at this point, what we did was we needed to not just let this stateless Postgres tier scale, we also needed efficient transaction processing and query processing by moving what some parts of the query did down to the storage layer or the distributed storage layer, because only then you'll get efficiency. So we started building these notions of shipping code and query processing and data processing to where the data is rather than the other way, along with a lot of tricks under the hood to make it efficient for over the network processing. So I'd say those two became the most important things. How do you recognize and move processing to close to data? And how do you, cut your network transfers and RPC calls? So we started focusing on those bits. All the while, we had built a transactional core, but we had to adapt the transactionality of our storage engine called DocDB, the lower half, to work in a very efficient manner for Postgres, along with some, even format changes, representation changes, and so on. So at the end of this whole exercise, if you just visualize what we had a logical upper service layer, which is kind of the query processing Postgres layer, borrowed from Postgres, but the lower half of which is modified to work against a distributed substrate. It's modified to work against distributed by pulling data remotely, but also pushing bits of query processing down. And the lower half had to be modified to accept these bits of push downs and do very, very efficient processing, right? So with this construct, we were able to really start scaling things. And then the rest of it is, of course, many hours of engineering and our lessons learned from running distributed systems, like, what constitutes P99, hey, this is a bad kind of failure. This type of an architecture will lead to correlated failures and so on and so forth. So, yeah.
Nice, Karthik, and building on that, Dmitri, question to you and picking up one of the great questions coming in from the audience here. Talk a little bit about performance. Again, we kind of heard Karthik talk about kind of the architecture and our goal to deliver performance. What are you seeing in the real world? Has this met your kind of performance at scale objectives that you had within your applications?
Performance is actually one of our performance always kind of goes against security, and security is our top priority, but we also need to scale. And as I was mentioning, we're processing a lot, and the overall volumes are just very large. So we can't compromise the security. So you must adhere to security, but you also always need to find a way to do proper performance. So in performance now, we're talking about proper partitioning of the data as one, and the second is actually how to do indexing, especially, I don't know, many probably have the same problem with NoSQL database. Secondary indexing practically non-existent, very hard to manage. If you're going after the exact partition with the primary key, many databases perform great. It's the complexity becomes is when you want to start going after secondary index data. And I know in many solutions you create like materialized views, there are index lookups. So you start building around the fact that you can't just go against secondary indexes. In the traditional SQL databases, secondary indexes are actually quite powerful because they handle creation of that view behind the scene for you. They grow and they manage differently, but the developer itself does not have to code for it. In NoSQL world, we kind of code for it. We have to query this to find the primary key, and then I can do parallel querying for every chunk of, especially if you do date-based processing. I need for this date range. Then your partitioning becoming kind of goofy. You partition by your primary key, but you also need to be able to find specific date ranges. So the secondary indexing often becomes like a logical solution that you need to solve. So I actually want to ask Karthik this, how do you guys solve the secondary indexing problem? I know many solve the primary index and partitioning. That's just classic random partitioning or whatever, regional partitioning or some custom partitioning. We all know how to do the primary key partitioning. It's the secondary indexes. I know in Cassandra, they used to refer to Solar indexes. In others, they do other indexing strategies. But in SQL, I just want to be able to say index this column. I don't want to know how you did it.
Yep.
But I want to hear how you guys actually do it.
Yeah. No, great question. Great question. So one of the most fundamental things we had built into Yugabyte as a distributed database when starting the database was this notion of distributed transactions, right? That's the core building block. And that's what required a lot of the architectural changes. Why, like we knew and had access to the code base of Cassandra and HBase that we knew intimately, right? Yeah, it's in Java, fine. We could translate it to C++ if we really needed, but that still wouldn't have solved the problem. So even though we had access to 2 production grade systems that are really good, we couldn't use anything, right? And that's basically, it comes down to this question. So the way we do this is, I mean, the most generic form of explaining this is if you have sharding of data across multiple nodes and you want to change the same row across 2 different nodes, right, or 2 different shards, if you can manage that atomically, you can pretty much use that mechanism to keep an index consistent with the primary table, right? So it could be like, so you have an insert into a primary table and you have an insert into an intern secondary index table, right? So first off, I guess at the highest level, whenever you create an index, you're creating an internally sharded and scaled out table implicitly, right? It has nothing to do with the way the original table is sharded and distributed across nodes. It can be completely reorganized, sharded and distributed a different way, right? So now that you have these tables, 1 per index and 1 for the primary table. So if you have 2 indexes, you'd have 3 internal tables and so on. The question now comes to whenever you do an operation on the primary table, you need to make some changes to the index table. Perhaps you have to insert, perhaps you have to update or delete and insert, like whatever, right? So you have to do some operations. So the question now boils down to how can you perform row updates across different tables in a transactional manner, right? In an atomic manner. Now, the problem that further complicates this is that there is no notion of time that is commonly shared across different nodes, right? Like, so each node can have its own time. And so you may do something at time equals 100 on node 1, but at the same instant, it's 95 on node 2 and 105 on node 3. And so no one can agree on when you actually made the change. It's a problem, right? So what we devised for this, like Google Spanner had solved this, but they used a GPS clock, you know, they're called true time. They do hardware-based synchronization to say the drift cannot be more than 7 milliseconds. And, you know, we were too poor to do that as a company. It's like, it's not going to be a viable database if we did that. So we said we would opt for a software-based solution called hybrid logical clock, where we exchange times and, you know, like both, we maintain both a logical clock, a Lamport clock, along with the physical clock, both in a 64-bit value, and we keep exchanging it with every RPC between the nodes, right? And so every node that takes part in a transaction is forced to exchange an RPC before the transaction gets committed, and that normalizes the time, and we can detect the time at which the transaction should be visible. So it's not in the past or the future of any node. All nodes know at what time they can surface this value, and so everybody can be consistent about it. Now, each of these shards replicates data using Raft, so it gives you the durability property and the availability because the data is replicated and highly available. So each statement of the transaction hits a Raft group, which is highly available. And across the Raft group, we use hybrid logical clocks to correlate time, right? So once we had this pattern down, again, this we built back in 2017, 18, so way back, but you don't want to make mess with this type of stuff. It has to absolutely work right, not just academically in theory, but by putting it to the test, right? So, Jepsen testing, failure testing, real-time production usage, a lot of stuff has gone into this. But once we had that down, now you can imagine the next layer of the cake as trying to interpret this user's schema and trying to do a variety of different transactions. For example, if you want a simple secondary index, yeah, you insert something into the primary table, you insert a corresponding row in the right shard on the right node in the secondary index table. So both of these appear transactionally. If you're doing let's say a unique index, well, then you have to add one more operation, which is you need to make sure this row in this value in the column doesn't already exist. So you'll be not just putting inserts, you'll also be putting reads. So you'll start doing more and more stuff to make it more complex operations on top. Now, the third layer of the puzzle, which was an entirely different framework, is how do you, like you said, build it on the fly? Because nobody really wants to know what happens. It's like, look, that column, interesting from now, just build that index, right? If you cannot build it on the fly, it's just no use. So that was another complex piece of engineering where you had to kind of build on the fly while data came in from any node, while making sure you don't drop a single value. So there's a whole framework for this that we have where we mark the point up to which we are rebuilding in the background. It's a distributed rebuild because all nodes have a piece of data. And then, we're able to play the changes that came in after. And just like Postgres, we keep the index because we want to be Postgres compatible while doing all this as well. So we keep this in a read-only state, which is a state that Postgres has in the system catalog. So sorry, write-only state. So the index table is write-only, not read-only. Cannot be read from until the full rebuild is completed, after which it switches to a read-write state, at which point you can read and write from it. So a lot of delicate pieces that had to fall in place. So I'd say those are the three-layer cake that kind of helped build this. So yeah, and this is precisely what I meant when I was just saying a lot of people asked for indexes on Cassandra, but and they were like, hey, how hard can it be? Just give me that one index. It's not a big deal, right? And we had built it to not have indexes, and we're like, oh, no, that's not that easy. I had to go all the way to the base and rebuild the thing.
So measurable SUs usually imply full data replication. So every additional view, you pretty much double up your data or add the data sets. What is the overhead of the secondary indexes in Yugabyte?
Yeah, so actually I'll answer that two ways. Firstly, every additional index only keeps a pointer by default, a pointer to the primary key or the row in the primary table, right? It's not all of the columns. So if you have a 50-column table and a 2-column like composite primary key index, then your each index will just keep those 2 columns in addition to whatever it is you're indexing by, because you need to keep that so you can go to the row. So that means by default, the storage overhead is low, but the query performance, so the CPU and the network overhead starts to increase, or not increase, it's a fixed amount, but you will go to the index table, retrieve the pointer, go to that row and retrieve what you want, unless you can satisfy it off the index. Now, we also support covering your columns or including additional columns into the index. So you can answer it straight off the index table, but here your storage would increase and your network and CPU would decrease, right? And now here's where the trade-off comes with respect to, are you in a public cloud environment or a private cloud environment? Typically what we've seen in public cloud environments, storage is cheap. You can attach any amount of storage to a node, right? You can attach more and more to it and make it dense, but CPU and network are both expensive. In fact, network is the most expensive by a mile, right? And in private cloud environments, network isn't as expensive because it's your network, it's free, right? But CPU and disk do the trade-off, and sometimes you cannot go more than a certain density because private clouds have a fixed cookie cutter size of machine. So depending on which cloud you go, here's where the application architecture would change. But I'd say On average, if you're doing a read, if you're satisfying it off the index, there's really no overhead. If you're doing a read where the index cannot satisfy everything, it's 2 RPCs instead of 1. So your latency will double, and there'll be a little bit more of a CPU hit depending on how much you do. If you're doing a write, each index adds an additional raft quorum consensus, right? So if you have 2 indexes, then you're writing to the primary table and to each of the indexes. It happens in parallel, so you might not see a latency hit necessarily. It might increase the P99, but it won't increase your average latency too much, but it will increase your resource consumption, right? Which is kind of the point of scaling out, though. You can scale out on number of indexes and everything by adding more nodes. The key thing to keep in mind, though, is that just by increasing the amount of data, the number of rows, you don't increase the amount of processing, because each row's update or insert hits a fixed number of raft groups, so a fixed number of machines, irrespective of the cluster size.
Awesome, Karthik. Dmitri, in the last few minutes here, let's maybe kind of quick lightning round of a couple key questions. One that's come in and one that I think is important. We've talked a lot about kind of the architecture, the design, the decision process, so kind of from the technology standpoint. But maybe talk very quickly about the relationship, kind of the partnership between Fiserv and Yugabyte from a support standpoint, your confidence in deploying this into your mission critical apps. Kind of how was that experience, and any kind of advice or kind of words of wisdom out to the audience that's in that similar evaluation phase?
So in Fiserv, there's a centralized procurement process for vendors onboarding. And then once you procure, you kind of become available for anybody within the Fiserv to participate. I believe, and I don't follow all lines of businesses, but I believe Yugabyte working across multiple lines of businesses today. For us specifically, we built 2 cloud databases, and we are now in process of building an on-prem copy for completely different purposes. So the completely independent applications. So the way we operate, once the security protocols and audit requirements and all of them satisfied, we implement the same. And I think in Yugabyte, you guys call it Yugabyte platform. Karthik, you probably can speak to it. I don't do much paperwork. I just know that when you do an enterprise relationship with Yugabyte, there is a separate platform offering. And what's the addition in the platform offering was the multi-cluster management, I believe.
Yep.
So instead of managing individual clusters by itself, you can create one operational model of how you're managing the multiple clusters. So the way we use our NoSQL, and Yugabyte falls for us in the category of NoSQL. Our NoSQL DBAs and our distributed application DBAs, they actually manage multiple vendors. They don't. It's not like you have a dedicated Yugabyte relationship. So from there, they come to each vendor, including Yugabyte, with their own operational requirements, which is even outside of what I do. The operational requirements, they may say, we want you to log here, we need the transaction log capture for that long for replay. We need to have a replication of disk in this way. So they actually work with the vendor specifically. And I know for you must set. So we haven't even talked about operational requirements, how hard we can be working operationally. But so what we talked about, the initial vendor evaluation, once you pass the evaluation, you go to procurement, where you allocate the number of licenses and everything else. And then you go into operation, what's the word? Making it operational.
The day 2 and day 2 operations, right? Yeah.
Yeah. So and then as I said, in operational, this is where they want to make a way to consistently manage multiple clusters, because the way the enterprise scale and the way we become efficient is we allow to share actual solutions. So a single DBA doesn't just manage one database. There's a group of DBAs that manages group of databases. So consistent operational models becomes also important. And this is where we talk about, I just need an SQL client to interact with multiple SQL databases. And Yugabyte is no different for me than any other SQL database. Same with CQL. As long as I know the CQL language, I can work with Cassandra or Yugabyte or any other SQL database. We now go into a document-based database, such as your Mongos and others, right? Consistency in including operations, right, is what we push all the vendors towards to. And this is why I'm saying we sometimes consider hard to work with, primarily because we're working with so many. We telling you our standards instead of accepting your solutions as is. Because for us to scale, we can't just have all kind of flavors of the same stuff, different ways, right? We drive through consistency, and it's actually primarily driven through security mandates, right? The patchings, the operating system level patching, the software level patching, like all the schedule, being able to coordinate all the different vendors and all different flavors adhere to that schedule. So operationally, it's also becomes sometimes a nightmare to manage if you allow to deviate from your standards. So we actually push, and even part of the Yugabyte contracts, you guys probably remember, negotiate the support model, right? How often we push the patches, how often do we release it? What's the maintenance, right? If I don't have any critical security vulnerabilities, I mean, I want to touch the system if it's operates successfully. So, as I said, one is the initial evaluation, make sure we satisfy all the security requirements. Production stability, this is your scaling, and when we talk about indexing, is how we can scale the data. And operational is final, is actually how you run it on a day-to-day operations and how hard it is to manage the day-to-day operations. Moreover, operationally, you must implement it in the different regions, in the different clouds, in the different internationally. And what we're trying to do is we're trying to actually push that model to be consistent. Because for us, the only way to be efficient is to have we call them a cookie cutter recipes, right? I solved this problem once, I don't want to solve it second time, right? So being able to, again, coding to standards, implementing to standards. When we talk about cloud, we heavily push for Kubernetes and deployments using the container strategies that are repeatable across multiple providers, Kubernetes providers, right?
And you guys definitely, held us to high standards, and really thank you for that. Really, it was a tough journey, but really helped us grow also. So really, thank you guys for all the. I mean, I know some people would say it's hard to work with, but we just say it's the right of earning business and the right and what is needed for your customers, frankly.
But I always say we're hard to work with on purpose, because at the end of the day, in the financial industry, sometimes it's often confused. When you're on your social media site, whatever your choice, you don't see your friends.
Yeah, they move very quickly, but the stakes are much smaller.
You never know about it, right? If we fail to post your check on your account, you kind of going to feel it.
Of course.
We take it at a different level, and all of the processes are there on purpose, because we do impact people's life, and we take it actually very seriously here internally. That's why we never go after the bleeding edge. We always going after the most secure and the most stable solutions, and it's all done on purpose.
Yeah,
nice. Dmitri, I know we're over time here. I want to squeeze in one more question, unless you really cut me off here. Just 30 seconds. I mean, what's next? What's kind of next on your journey with YugabyteDB? How kind of and in plans?
So we implemented, to be honest, we implement on a very small scale. And as I was saying, for us, we want to build small and grow bigger. So what we have not experienced yet, because we're just in such early stages of integration, is we didn't experience the growth. But what we notice in other applications is when we reach the capacity, it's very hard for us to actually allocate more quickly, react quickly. It's a whole project for us to do an expansion, infrastructure allocation. So what we have not experienced yet is that dynamic growth that we all after, right? So what we're looking for as the data sets grow, because as you know, in financial industry, you have to minimum 7 years retention and stuff like this. We only been in here, I think, 1.5 years, 2 years. We built our first cluster 1.5 years ago. So we have not experienced the 7 years of accumulation. So what we're actually talking about is closely monitor and see how we can grow, right? And then see if these processes are actually repeatable. And the other thing is we want what we call the fail fast. We want to try projects, launch something, and make it disappear if it's a failure, right? So fail fast, creating quick solutions on demand. And if they don't work out, being able to eliminate it. And this is where the power of the cloud and dynamic compute allocations, if you're not happy with some, you want to be able to shut down next day and make it disappear. Because, with traditional infrastructure allocation, if you build an entire data center worth of servers, and all of a sudden the product is not no-go, you have your sunk cost.
Millions of dollars in investment.
We haven't even started talking about the cost management. I know kind of took the technical path took longer than we wanted, but I hope that was valuable to everyone. So.
Awesome, Dmitri. Then with that, I know we can keep on going. There's a ton more stuff we could ask, but we're gonna cut it off there. And then we're a little bit over time. So again, a big thank you, Dmitri, for joining us today. It was great to get these insights, and Karthik, thanks. It was a good balance of kind of, again, behind the scenes and what Dmitri's Fiserv is doing in the real world. To everyone out there that joined us, again, a big thank you for joining in. If you have more questions, hop on over to Slack, join our group in Slack, or if you're inspired to try something today, start playing in your lab, go to cloud.yugabyte.com, sign up for our managed service. You can get started for free, no credit card, and just start playing with it. Is the best way to experience. We're here to help, so reach out anytime. Thank you again for joining us, and we hope to be working with all of you soon. Thank you.
Thank you, guys.
Thanks, Dmitri. Yeah, and thanks, Michael.
Have a good day.
Yep. Bye, everyone.
Bye.